All right, welcome in. We have one last video here for chapter 8 on thermodynamics. In this video, we will look at Gibbs free energy as a way to predict spontaneity. We will be able to calculate delta G using a variety of strategies, and we'll be able to relate it to our equilibrium constant. Previously, we said we can predict the spontaneity of reactions by looking at the entropy in the universe. The entropy in the universe has to increase in order for our reactions to occur spontaneously. This is a little bit of a daunting task and a little bit misleading if we're thinking about ice. Ice is going to form when water freezes, which is going to decrease the entropy of our water. If this process decreases the entropy of the water, how does it occur spontaneously? Well, it occurs spontaneously at low temperatures, and because we have to care about more than just our system, we also have to consider the surroundings, because spontaneity is based on the entropy of the entire universe increasing, not just our system. We can state this as our second law of thermodynamics again. The entropy of the universe increases. Well, the entropy of our surroundings depends on the temperature. If we have an endothermic process, this will absorb energy from the surroundings. In order for an endothermic process to happen, we need to decrease the entropy of our surroundings because there is less energy in the surroundings. With less energy, there are going to be fewer microstates and therefore less entropy. Exothermic processes are the reverse. When exothermic processes occur, energy is released into the surroundings, which increases the temperature of the surroundings. When there's a higher temperature, more energy in the surroundings, there is more entropy as well. More ways to shuffle around that energy when there's just more energy around. We can look at an example. Here we have candles burning. We know that the enthalpy of this reaction is negative. In fact, it's negative 1,600 kilojoules for the reaction balanced here, because we're releasing heat. When we burn things, we release heat. Because of this, the energy is released to the surroundings, and the temperature of the surroundings increases. Therefore, the entropy of the surroundings increases. We can also think about the entropy of our system based on our balanced reaction. We said in our previous video, the first thing to check is the phase. In this balanced reaction, we have 51 moles of gas on the product side and just 38 moles of gas on the reactant side. Since we're increasing the amount of gas by a huge amount, we also are increasing the amount of entropy by a huge amount. When the entropy change for our system is positive and the entropy change for our surroundings is positive, we have to increase the entropy of the universe. This is going to be spontaneous. And in fact, this is what we see. As soon as we start this reaction happening, it will continue happening. One thing we can infer from our ice example is that the change in entropy for the surroundings is going to depend on the temperature. We know that ice forming can be spontaneous if it's very cold. But we also know that ice forming can also not be spontaneous if it's much hotter. Right? The cutoff is about 0 degrees Celsius, the freezing point of water. Below that point, it's spontaneous. Above it, it's not spontaneous. The reason that this is the case is because we have these two competing factors: the entropy change for our system and the entropy change for our surroundings. We can quantify this. The change in entropy for our surroundings is going to be related to the change in enthalpy for our system divided by the temperature, and we'll multiply by -1 to make sure that our sign conventions match up. We end up with this expression: negative delta H over T for our system is equal to the change in entropy for our surroundings. Our expression for spontaneity is now, okay, delta S for the universe is equal to delta S for our system plus our surroundings. Let's replace our delta S for the surroundings with negative delta H divided by T. Now we can think about things purely in terms of our system. We don't need to worry about the entire universe if we're framing things in this way. If we're able to get away with only thinking about the chemicals in our reaction instead of the entire universe, that's better. This is going to be easier to wrap our mind around, easier to do calculations with. We can take this expression and we can reframe it a little bit and make our lives perhaps a little bit easier. What we're going to do is we're going to multiply this bottom equation by negative t. This is the same equation, just reframed, but we'll see it in this form a little bit more often. The reason being is because this negative t times delta S of the universe has a different name. We can call this Gibbs free energy. Gibbs free energy has the symbol G, or delta G for the change in Gibbs free energy. And it's another metric for when our reactions are spontaneous. The good news here is that instead of having to deal with the entire universe, Gibbs free energy is only in terms of our system. We have that equation that we wrote down on the previous slide. The enthalpy of our system minus temperature times the entropy for our system as our change in Gibbs free energy. For the entropy of the universe, we were trying to make that positive. For Gibbs free energy, since we've multiplied by negative t, well, for spontaneous reactions, delta G is going to be negative. We can use our equation for delta G to predict when our reactions are spontaneous. If we know the signs of our change in enthalpy and change in entropy, we can use our equation, we can use our intuition to figure out when our delta G will be negative, which implies our reaction is spontaneous. In order for delta G to be negative, we would like our delta H to be negative. Since we're subtracting temperature times change in entropy, we would like this delta S to be positive. If we have both of those conditions met, delta H is negative, delta S is positive, that means our reaction has to be spontaneous. A negative number minus a positive number is going to be negative, is going to be spontaneous. The inverse will also be true. If we have a positive enthalpy and a negative change in entropy, a positive number minus a negative number will always be positive. When delta H is positive and delta S is negative, our reaction can't be spontaneous. The other two options, when delta H and delta S have the same sign, well, it depends on the temperature. We have two competing factors, delta H if it's negative, and delta S if it's also negative. A negative number minus a negative number is, well, it depends. Sometimes negative, sometimes positive. If our temperature is small enough, our delta H term can outweigh our delta S term. And so at low temperatures, negative delta H, negative delta S will be spontaneous. Again, the inverse logic also holds true. If we have a positive delta H and a positive delta S, a positive number minus a positive number, well, this is sometimes negative, sometimes positive. When we have a large temperature, we can subtract a bigger number and end up with a delta G that is negative. Positive delta H, positive delta S, can be spontaneous at high temperatures. We can look at this qualitatively. We can also look at this quantitatively. We have Hess's law to try to figure out the delta H of our system, or perhaps calorimetry to figure this out experimentally. We have Hess's law again to figure out delta S for our system. If we know the temperature and these two thermodynamic properties, then we can figure out our delta G and if our reaction is spontaneous. Alternatively, we can also figure out maybe the temperature at which our reaction might become spontaneous. If we know delta H and we know delta S, we can find the temperature where our Gibbs free energy changes from negative to positive, or vice versa. Let's do a couple of qualitative examples. For this first reaction, we know that our delta H is negative. We have an exothermic process. What can we find about the delta S for this reaction? Well, looking at the balanced reaction, we have 6 moles of gas turning into 7 moles of gas. It seems like we're increasing the amount of gas, which means we should be increasing the amount of entropy. In our equation, we get a negative delta H minus a positive delta S. Delta G has to be negative, which means this reaction is always spontaneous. For our second reaction, we know the delta H is positive. We have an endothermic reaction. And looking at our amount of gas on each side, we have 1 mole of gas turning into 3 moles of gas. This should be a reaction that increases its entropy. Now we have a positive value for delta H and a positive value for delta S. Endothermic reactions are not helping us to be spontaneous, but this increase in entropy is helping us to be spontaneous. Our second term will outweigh the first term when we have high temperatures. Positive H, positive S means that we need a large temperature. In order to be quantitative, well, we have a few ways we can calculate our delta G. The first is kind of what we mentioned on the previous slide. We can try to calculate delta H, calculate delta S, maybe using our Hess's law ideas and some tabulated values. Right, we have a handout full of delta H of formations, full of standard molar entropies, which we can use to find our delta H and delta S for our reaction. From there, if we know the temperature, we can figure out the value for delta G. This strategy is great when we have our chemicals on our handout of standard values and when we have our temperature relatively constant. It's also good at, well, a variety of temperatures. Perfect. Occasionally, we can use a shortcut. Also on our handout of tabulated thermodynamic values, we have delta G of formation, the Gibbs free energy of formation. These values are good when we are at 298 Kelvin. Right? These tabulated values for delta G, they do depend on the temperature. On our handout, those values are at a temperature of 298 Kelvin. This method is a little bit faster. We don't have to figure out 2 values to get our third value. We can just do this in a single step. But we do need to be at a constant temperature, specifically of 298 Kelvin. One last method that we can introduce, delta G is a state function. We can use all of our Hess's laws ideas for delta G. Maybe we have the delta G for a series of steps in our mechanism that add up to some total reaction that we care about. Well, perfect. We can do Hess's law with Gibbs free energy as well. A few extra details about our second method on that previous slide. We can use our delta G of formation. Delta G of formation is defined as how much free energy is there when we form 1 mole of a chemical from its constituent elements in their most common stable forms at standard conditions. So for example, if we're thinking about liquid water, we're trying to form 1 mole of liquid water from its pure elements at standard conditions. These elements exist as hydrogen gas and oxygen gas. All that's left to do is balance this. This is the reaction that we're thinking about. The delta G for this reaction is exactly the delta G of formation for H2O liquid. As a quick reminder, our standard states, our standard conditions, gases need to have a pressure of 1 atm, solutions need to have a concentration of 1 molar, and our temperature is almost always 298 Kelvin. We can look at a quantitative example for a moment. Here we have the addition reaction for C2H4. This is ethene turning into ethane by combining with hydrogen gas. In this case, we're given the delta H for this reaction, and we are given the delta S for this reaction. You might imagine a question where we're not given these values, but we could find them using our handout of enthalpy of formation and standard molar entropy values, and calculating delta H as a first step, calculating delta S as a second step. Once we have these, though, we can use them to find our value for delta G. Gibbs free energy is enthalpy minus temperature times our entropy. Notably here, delta H is often in kilojoules. Delta S is often in joules per Kelvin. This is fine, but if we're subtracting these values from each other, we need to make sure that those units line up. We can either change this value to joules, or we can change this values to kilojoules per Kelvin. Either is okay. This looks better. Now we can be subtracting kilojoules from kilojoules, and we can end up with a value. We get this result, negative 100.4 kilojoules, which is negative, which means our reaction is spontaneous. Our follow-up question. We can find the temperature where Gibbs free energy is exactly equal to 0. This will be the temperature where our reaction changes from spontaneous to not spontaneous. We can see here that we have a negative enthalpy and a negative entropy, which means our reaction will only be spontaneous at low temperatures, below a certain temperature. This question B will determine exactly what that cutoff is for temperature to be considered high or low for this particular reaction. Our answer here is 1130 Kelvin. This is the point where delta G is exactly 0. We said our reaction will only happen at low temperatures. This is our cutoff point. This reaction will be spontaneous at temperatures below 1130 Kelvin. Above this temperature, our reaction will not be spontaneous. Another useful definition of Gibbs free energy is that it is the maximum amount of energy that is available to do work. When our reactions produce some amount of energy, some of that energy has to go towards increasing the disorder of the universe. Our free energy tells us how much energy is available to do some sort of work. Here we're talking about work in the physics sense, applying some force over a distance, or perhaps using it to drive other reactions. Because we have to increase the entropy of our universe, no system will be 100% efficient. We're always going to lose some energy to our surroundings via heat or resistance, etc. We can consider a hypothetical case where we are not doing that. This is considered a reversible reaction where all energy is captured by our reaction and we can be at equilibrium every single moment of this reaction. This is a hypothetical situation, but it's a useful approximation when we're doing some calculations. To this point, we have been dealing with standard conditions. I haven't always been drawing it, but our symbol here, the little circle, implies that we're at standard conditions. Our formulas so far have been using this standard conditions symbolism. When that symbol is present, we have solutions at 1 molar, we have pressures at 1 atm, and our temperature, unless otherwise specified, is going to be 298 Kelvin. Most of our reactions in real life are not at these conditions. And so we need to be able to adapt for that. In order to do so, we have this nice equation. The change in free energy at non-standard conditions is equal to our standard change in free energy plus the gas constant times the temperature times the natural log of our reaction quotient. This is the same Q that we've been using in our equilibrium discussions. It's the law of mass action, the ratio of products divided by reactants, where any coefficients turn into exponents. Because this new equation invokes the reaction quotient, we can relate our Gibbs free energy to equilibrium. If our reaction is at equilibrium, if our system is at equilibrium, then our reaction quotient has to be exactly equal to the equilibrium constant. Additionally, if we are at equilibrium, then our change in free energy is going to be exactly 0. We're not going to spontaneously do the forward reaction, and we're not going to spontaneously do the reverse reaction. At equilibrium, we're doing both reactions in equal amount, and our reaction doesn't shift one way or the other. It remains where it is. It remains with those steady concentrations. And so when we are at equilibrium, we can replace our Q with K, and we can replace our delta G with 0. We can simplify this expression to this new equation. At equilibrium, we have delta G at standard conditions is equal to negative RT times the natural log of K, the equilibrium constant. This is fantastic. We love our equilibrium material. Now we can shift back and get back to talking about equilibrium. Now in the context of delta G and free energy and thermodynamics. We've actually already seen this kind of relationship in the past. We know that our equilibrium constant depends on the temperature, and we had our Van Hoft equation to explain that. Well, now we can see where this Van Hoft equation comes from. If we rearrange our new delta G equation, we can solve for K in terms of delta G. The equilibrium constant is equal to E raised to the negative delta G divided by RT. This is why our equilibrium constant changes at different temperatures. Since we know our Gibbs free energy is related to the change in enthalpy and entropy, we can sub this into our equation and end up with our Van Hoft expression. We can have a variety of forms of this Van Hoft equation. We utilize this form in our experiment on cobalt complexes in equilibrium with each other at various temperatures. But we can also have a form that is useful when we have more than 2 data points. This can form a linear relationship between the natural log of our equilibrium constant and 1 over temperature, and we can figure out the change in enthalpy based on the slope, the change in entropy based on the y-intercept. Or if we're at a single temperature, we have this expression relating our equilibrium constant to both enthalpy and entropy. We have a practice problem here. I'm going to leave this as practice, but I'll put up the answer so that you can check. One last practice problem. We can use some experimental data to figure out our change in enthalpy and entropy graphically. Here, we've been able to measure our equilibrium constant at a variety of temperatures. Our Van Hoft equation relates the equilibrium constant to these thermodynamic properties. All we need to do is graph natural log of the equilibrium constant as our y variable, 1 over temperature as our x variable. If we get this data into Excel or another graphing program, we can get a line of best fit. And it should be something like this. Y is equal to negative 13704 times x plus 75.04. To solve this, our slope has to be equal to negative delta H divided by the gas constant, R. We can get this value 1.14 times 10 to the 5th joules, or about 114 kilojoules. Likewise, we can use our y-intercept to help us find delta S. We can find our answer. The change in entropy for this reaction is 624 joules per Kelvin. All right, I think we have achieved our goals. We have our new thermodynamic property known as Gibbs free energy, which is another metric for whether our reaction is spontaneous or not. We have a variety of techniques to calculate our delta G and determine whether this reaction is spontaneous, and we can even relate this back to our equilibrium processes. Thanks for being here. Thanks for listening. Let me know if you have any questions, and I look forward to seeing you in the next video.